Episode 11, Saturday Specials, Kirchhoff and the Laws That Shaped Electronics. Series, Crash Course Instrumentation. Saturday Specials, Cold Open. What if two simple sentences could explain almost every circuit you will ever touch? Today, we meet Gustav Kirchhoff and the thinkers around him, the crew who turned messy wires into a predictable science. And we will discover how two ideas unlocked everything from telegraphs to integrated circuits. The setup, before Kirchhoff. In the early 1800s, experimenters were swimming in discoveries, but starving for rules. Georg Ohm linked current, voltage, and resistance in the 1820s. André-Marie Ampère showed that electric current and magnetism are inseparable. Michael Faraday revealed electromagnetic induction, turning motion into electricity and electricity back into motion. Wonderful, but how do you predict multiple components tied together into a real network? That is where Kirchhoff enters. Meet Gustav Kirchhoff. Gustav Robert Kirchhoff, born in 1824, studied at Königsberg and published his circuit rules in 1845 while still a student. He later teamed with Robert Bunsen to pioneer spectroscopy, identifying new elements by their light signatures, an unexpected twist that shows how broadly he thought. But his most widely used gift to technicians and engineers are two plain language laws about currents at a junction and voltages around a loop. Law 1, the current law, the node rule. At any junction of conductors, what flows in must flow out. In practice, that means the total current entering a node equals the total current leaving that node. If you prefer a picture, imagine water pipes meeting at a T. The flow cannot pile up at the joint, it divides or combines, but it balances. This rule lets you check measurements and design branches that share current without surprises. Law 2, the voltage law, the loop rule. Follow any closed path through a circuit. The total pushes up from sources equal the total drops across components. Said another way, a loop begins and ends at the same electrical potential, so every rise is paid for by a matching set of drops. That simple idea makes series voltage drops predictable and keeps power accounting honest. Why these two laws changed everything. Together, the node rule and the loop rule turn a tangled schematic into a solvable puzzle. They allow engineers to break a complex network into loops and junctions, then compute currents, voltages, and power with certainty. That certainty scaled the world. Long telegraph lines, city lighting grids, telephone exchanges, radio receivers, control panels, and modern printed circuit boards all rely on these two sentences. Counterparts and collaborators who closed the circle. Georg Ohm gave the proportional link between voltage, current, and resistance, essential arithmetic inside every Kirchhoff problem. Michael Faraday connected electricity and magnetism and gave us induction. Without Faraday's insight, no transformers, no generators, no motors. James Clerk. Maxwell unified the field with equations that predicted radio itself. His work told us why circuits radiate and how signals move. Léon Charles Thévenin showed that an entire network can be replaced by one ideal source and a single resistance, simplifying design and troubleshooting. Edward Laurie Norton mirrored that idea with a current source and a parallel resistance, two ways to look at the same reality that pair perfectly with Kirchhoff's rules. James Prescott. Joule linked current and heat in conductors, reminding us that power loss is not just numbers, it is temperature rise and failure if you ignore it. And do not forget Robert Bunsen working with Kirchhoff on spectroscopy. Their method discovered cesium and rubidium, proving that careful measurement could reveal hidden structure everywhere, not only in circuits. A short story from the 19th century. Picture the 1840s. Copper wires stretch across towns, batteries that leak, instruments made by hand, and no textbook that says how networks behave. Kirchhoff writes down two balancing acts. Currents at a node, voltages around a loop, and suddenly students have a method and craftsmen have a checklist. Within 2 decades, Maxwell's work predicts radio. By the 1880s, equivalent circuits appear. By the 1920s, vacuum tube radios and early amplifiers are more than magic. They are engineering. Mental models you can keep forever. For the node rule, imagine coloring every connection point in a schematic. Wherever wires share the same color, no charge is stored long term. What arrives must depart. For the loop rule, draw a path and keep a running notebook in words. Rise here, drop there, and end where you began. If the numbers do not balance, the model or the measurement is wrong. These two habits train your eyes to find mistakes before they become expensive. How this revolution shows up in your work today. When you parallel devices in a control panel and expect predictable current sharing, you are trusting the node rule. When you count each voltage drop in a series chain and compare it to the source, you are trusting the loop rule. When you use a thévenin or Norton equivalent to replace a messy subcircuit, you are honoring the same conservation ideas. When you size conductors and fuses to limit heat and faults, you are applying Joule's warning about power and the real-world limits those drops represent. Quick recap, sticky in plain words. What flows in must flow out at any junction. What rises and what drops around a closed path must balance. Ohm solves the branches, Kirchhoff balances the network, Maxwell tells you how fields move, and Thévenin and Norton let you swap a jungle of parts for a simple source and resistance. Outro. 2 rules, many minds, and a century of breakthroughs. That is how messy wires became modern electronics. If this helped, please like and subscribe so you never miss a Crash Course Instrumentation episode. Special thanks to Tony Kuphaldt and the open source community for making world-class learning materials freely available.